It's fun.
It's ready.
Awesome.
So I will introduce you, and I don't have any bios about you.
Yeah, I don't know.
We can buy over ourselves,
I'm like, I have to ask that.
Well, I will be.
Yeah. Okay.
How are you? Maybe we just.
Sitting here? Yeah. Okay, good. Well, I said I just said you were I think you missed fiction. I missed it.
That works.
Oh, the Eclipse will be able to license plate that says something. It's me. Oh, very good. You're internet famous. Yeah.
Nice to meet you.
What's your name?
Rick Yeames.
Oh, yeah, Rick Eames,
Are you guys working with Sally Jensen?
Not well. I am a little bit. It's
Okay.
more the physics professor Brad Moser.
Right,
Working
right.
more directly with her because the three of us, along with a bunch of other students, are going to Pittsburgh, New Hampshire for the eclipse.
Okay,
So
that's
not
where
gonna
we're
be-
gonna be.
Yeah, great.
Okay, do you have a balloon going up there?
Yeah, we're going to be releasing a total of 60 weather balloons.
From Pittsburgh?
Yeah. Yeah.
Okay, so we have to talk because we're gonna be up, where are you staying?
We're staying at the what's it called? Northern Trails Adventure Lodge.
Okay, okay,
Yeah.
okay.
It's 2 months. It's right in the bend of Route 3 before it departs Lake Francis and goes north.
Yeah, yeah, so totality, 3 minutes, 10 seconds?
Yeah.
Very good. Well,
Where will you
if
be
we
in
get,
Pittsburgh?
Mountain View Cabins, right across from Young's store.
I'm not familiar with the area too much.
It's right on Route 3.
Yeah.
I have,
Everything
actually,
is.
well, we have 11 bedrooms. So I'll have a group of about 20 to 30. I applied for a grant. Rick Feinberg, are you working, do you work with, you're a NASA partner, I assume?
Yeah.
Okay, so who's your, Kelly Corrick, who's your main partner in the Eclipses?
Well, this is a grant funded by NASA, and Montana State University is the lead organization. And there's another 40, 50 organizations working under this.
Okay.
Yeah.
How many balloons are you sending out? It's a lot.
Approximately 600
How many locations?
at 19. Well,
See, we got
about
to talk
15
because,
locations.
and here's the scoop. I've connected with the BVI community, blind visually impaired. So if it's cloudy, which in Pittsburgh early April is a 50-50 shot, we want to have some BVI folks lead us in non-visual ways of experiencing the eclipse. We have sonification, we have tactiles. Dr. Cass and David Hurd put out a tactile pamphlet on it with Braille. I wanted to connect to some of the people I work with the BVI community. Know her, Wanda Diaz-Merced, the blind astrophysicist from NASA. So I'm hoping maybe to get her to New Hampshire. But these folks never see the eclipse, they always have to experience it. So how cool is it to transform the sight of a lifetime for many of us into an event of a lifetime for all of us? And if it's cloudy, it's just an opportunity. So we'll definitely have to talk. I'll get you. I want to show you guys the eclipse mobile. And I can make you eclipse knots. Not as cool as an astronaut, but easier, much cheaper, and less motion sickness.
Yeah,
There you
yeah.
go. Okay, sounds good.
Good to meet you, Rick.
Well, good evening, ladies and gentlemen. Welcome to McAuliffe-Shepard Discovery Center. We're so happy that you've chosen to take some of the time of your evening, this Friday evening, with a great weekend coming up, to come here to enjoy our Superstellar Friday. And as you know, we have a Superstellar Friday every first Friday of every month. So stay tuned for Star Up. I'm sure you're familiar, starhop.com. That's all you need to know. That's your website for the universe. So it gives me great pleasure to introduce our speaker this evening and the topic at hand. Solar eclipses, have puzzled people for over 10,000 years, wondering what makes them happen. They come, they go. What is that going on in the sky? Well, we can use science to figure out what's going on. And as a matter of fact, we can use meteorology to figure out what's going on. And not only can we figure out what's going on in the past, but we can look forward to and look into the future and use meteorology to predict even what might be going on in the solar eclipse Monday, April 8th, 2024, which is not that many days away.
63.
63 days. Not that anybody's counting. So to my far left is Jacob Garside, and he's currently a second-year student at Plymouth State University and is getting his Bachelor of Science in Meteorology. And he's been a part of the Nationwide Eclipse Ballooning Project since 2022. And he's also a space grant recipient and an intern at the Discovery Center during this past summer of 2023. And his campers that he had, 15 or so of them, are well prepared for the April 8th eclipse coming up. And Jacob is also coming along with Genevieve Picciano. Did I do okay? Within a Master of Science in the Applied Meteorology, coming right up. And then Professor Eric Kelsey, Meteorology Research Professor, and we welcome everybody to the stage here for the McAuliffe-Shepard Discovery Center Superstellar Friday evening. How about a round of applause? So Jacob, I'll let you start, and whoever's starting. I wasn't told that part.
I guess that'll be me. I'll break the ice for the students, make it a little
Excuse
easier
me.
on them. And aren't we glad that we live in this day and age where come April 8th, we don't have to sacrifice anybody in order to bring the sun back? Yes, good. We can just all enjoy it and live to tell about it. So welcome. Yeah, I'm Eric Kelsey. Thank you for the great introduction. And I'm going to start things off by just telling a little bit about myself, and then Genevieve and Jacob will talk a little bit more about themselves so you can get to know us a little bit. I'll give an overview of this NASA-funded program that we're a part of, and I'm going to leave Genevieve and Jacob, two stellar students at Plymouth State in meteorology, to talk about the project that we're doing and everything, all the activities we're doing and that we did in October for the annular eclipse and the one coming up, of course, on April 8th. So I'm from Nashua originally. I grew up there, and I got into meteorology basically because of snowstorms. I love any kind of weather really, but snowstorms, big nor'easters are what got me really into the weather, and I was always glued to the TV, watching the Weather Channel and Harvey Leonard and other folks on TV, mostly out of Boston, talking about the next big snowstorm. So ever since I was this big, I knew I wanted to go into meteorology. I was lucky enough to find a job back in my home state where we get a lot of snow. Because I learned going out to Missouri for college, I learned why a lot of the country doesn't like winter. It's brown and cold all winter. Yeah, there's nothing fun to do. So I made my way back up here and got a really cool job at Plymouth State in the meteorology program. I really enjoy curling. So in Plymouth, at the ice arena there, we have a curling club. So I usually yell at my other professors on my team, which is kind of fun. They're older than me. Gives me an excuse to yell at them. I like baseball, really playing any sports. I love cooking and baking. Teaching, of course, hiking, skiing. I'm an active person. I love being outdoors. So that's me in a nutshell. Campaigns like this that we're going to talk to you about, brings you outside and seeing this really phenomenal natural phenomenon that's going on. And so this just fits right in with my personality and what I like to do. All right, enough about me.
Who am I? I'm Jacob Garside. I am a second-year meteorology student. I got into meteorology simply because I liked clouds, and I didn't realize how hard meteorology really is. I'm in Calculus 3 right now. I'm trying to get through that. Physics 2, thermodynamics. It's a lot of fun. I'm from Concord. Well, I'm not from Concord, but I live in Concord now when I'm not at Plymouth State University. Like Dave said, I was an employee here over the summer. I was a NASA Space Grant recipient and an intern here, which was great. And I came back over winter break to do a little bit of work, so I had a lot of fun with that.
All right, and then I am over here on the left side of this picture. There's on the left side. I'm a second-year applied meteorology student, getting my master's. I'm from Enval, New York, which is upstate New York. Outside of meteorology in the classroom, I like to play the euphonium, which is like a small tuba. I guess I got into weather because I just really liked earth science in high school, and then I also liked watching the Weather Channel, not because I really enjoyed what was going on, but because the pictures moved and they looked cool.
All right, so I'll give you a broad overview of the project that we are part of. We are part of the Nationwide Eclipse Ballooning Project, which is funded by NASA. And Montana State University is the lead organization on it. They've actually gone out and studied with weather balloons and other instruments previous eclipses. And with this pairing of eclipses, only 6 months apart, the last one being October 14th, hitting the western US with an annular eclipse, and then the one on April 8th, they saw a great opportunity to really reach the masses. With this, right? This is something that virtually everyone in the US can witness, hopefully there aren't any clouds, and be a part of and learn a lot about, and just be really excited about something, you know, going on out there in nature. And so Montana State led this effort to engage college students and the broader public through weather ballooning. So sending up weather balloons to study how the atmosphere changes during an eclipse. It's like a rapid onset of night and then a rapid onset of daytime again, resuming of daytime. Is essentially what it is. Yeah, I mentioned before, Montana State has been involved in previous eclipses. So there was the big one in the US in 2017, you might remember that. I was out in Missouri for that. By my alma mater, and that was the first time I had seen a total solar eclipse. And how many here have seen a total solar eclipse? A good number of you. Awesome. Okay, yeah. It is otherworldly. There is this pitch black hole in the sky, and you see this beautiful corona streaming out from it, and you can see stars around it, and then it looks like a sunset everywhere you look around the horizon. It is just incredible. And that's why I jumped on this project at a heartbeat, because I want to study it, I want to see another one, and it's just great that it happens to be here in our home state, not too far to the north. So there's this experience by some of the institutions on this project, and so they really built it out so that more people can be involved, more colleges. And through this project, we're going to have about, as you'll see in a later slide, we got 19 teams launching weather balloons and across the eclipse path. And this is by far the biggest data set of weather data collected through the atmosphere for an eclipse. This is just a lot of measurements that we're taking. And some of the research questions that we'd like to answer are, what's going on up in the stratosphere? So, you know, down here near the ground, we kind of have a good idea of what's going to happen, right? What do you think might happen down here near the ground during the eclipse? Dark and colder, right? That's one of the big things that we should feel, especially if there aren't any clouds, right? You turn off the sun, it's like going into night, the air is going to cool off. So we know that pretty well, but we're going to get even more measurements of that down low. But up in the stratosphere, there's the ozone layer, and the ozone layer absorbs UV radiation from the sun. And so when you turn off the UV radiation during the eclipse, well, that ozone layer doesn't warm up anymore, it starts to cool off, just like down here. And when that happens, imagine waves form, and imagine sticking your finger in a puddle and or a pond, a still pond, and moving it, right? Waves will emanate away from the path of your finger, and that's exactly what happens up in the stratosphere, but we just can't see it because there aren't any clouds up there to actually see the waves. But we know they're there, and in the last couple of eclipses, they were actually confirmed to exist for the first time, so that's really exciting. And now with more weather balloons going up into the stratosphere, we'll be able to get better measurements of it and better understand what's going on up there and how they might affect the stratosphere and maybe even the weather down here where we live in the troposphere. So those are some of the big things that we'd like to learn from it, and Genevieve will talk a little bit about how she's gonna use weather models to simulate the eclipse and see how well they perform during eclipses. All right, here are the logos that Genevieve, I think it was Genevieve, put together. Yes, thank you, Genevieve. All of the organizations participating in this project. It is a lot, including some high schools too. In fact, Hanover High School here in New Hampshire is involved in it. And there's us from the state. But yeah, people, institutions from across the country are involved. And here's where they're from. So we have atmospheric science teams, that's what we are. We're launching weather balloons. And then we have engineering teams in orange, and they are going to be launching a slightly different balloon. It's a little bit bigger, and they're developing custom payloads for their balloons. And so they'll send them up to about 100,000 feet or so, and they're going to hope that they will cross under the shadow of the moon during the eclipse and take pictures, video, other measurements. That's not what we're doing, so I can't speak very much to exactly what they're doing, but that's the gist of it. Engineering kind of stuff. Oh, thanks for pushing it along. So what we are doing is we are going to be launching balloons once an hour for 30 hours. And technically, Plymouth State has 2 teams. We had enough funding to recruit enough students for 2 teams. So, but we're going to act kind of as one, but we're going to launch twice the number of balloons. So we're going to actually launch 60 balloons up in Pittsburgh once every 30 minutes.
Wow.
For 30 hours. Yeah, it's a lot of balloons. They have these little instruments on them called radiosondes, and actually I don't want to spoil it too much, but I saw radiosondes in there, so that's what that is, the little instrument package. And we're going to start 24 hours ahead of time before the eclipse to get to capture a picture of what the atmosphere is doing before the eclipse. You know, how's it behaving before the eclipse? What kind of waves are up in the stratosphere before the eclipse? So we can differentiate those from the eclipse-driven stratospheric waves. And then we're going to continue launching for another 6 hours after totality, and so we can see what the atmosphere does because of the eclipse. And we're going to have a surface weather station as well to take ground measurements, or measurements at about eye level, face level. And then I mentioned briefly the engineering teams, so I don't think I need to dwell on that any longer. And I think the next slide is for you.
So before we get into the science of it, here are our teams. So Plymouth State University is the only university or school with 2 teams, 2 atmospheric science teams. So we have 10 meteorology students. One of those is me, one of those is Genevieve. 5 art and design, which we are the only team with art, which is pretty interesting. We'll get into that a little bit later. We have a climate studies student, a political science student. You can see the grade level there. The reason there's no freshmen is because this project's been going on forever. I was a freshman when I was picked, but these are the updated versions of this. And then just a little picture of our team there. So these are all pictures. I put together this slide the other day. We traveled to Albuquerque, New Mexico, and then we drove east 40 miles to Moriarty. There'll be a map later. That's us in the airport. We made it all the way there. That's me doing some Calc 2 in the lobby of the hotel that we were in. The town of Moriarty was great. They let us use their soccer fields and football fields, and we set up a bunch of tents. They let us use some old portable classrooms, so we were able to have some shelter during the night, and we had places to put how many helium tanks did we have?
Ooh, I think we had about 30.
30 helium tanks. Have you guys ever seen those? They're this tall, real heavy. I had one fall on me. Not a good time. But that was just some of our traveling right there. Some more pictures of our team. So that's us launching balloons. We were out all night long. 30 hours means we were out all night. It was cold, very cold in New Mexico. We did a bunch of outreach. I know this picture is kind of grainy here, but we had hundreds of students come to see us, which was great. And we let them launch the balloons. It was just a great time. We had people driving over an hour to come see us, right? Most of these people had never seen a weather balloon before, so it was really interesting to be able to bring that to that community. The art section here, so Dr. Kelsey can probably talk a little bit more about this, but specifically what you're seeing here, because we had those 5 art students, they wanted to get a little bit of credit, and they wanted to bring this different perspective to what we were doing. So they made art during the eclipse. There's that paper there is actually paper with a UV reactant dye on it. They're called cyanotypes. So during the eclipse leaves these little prints. This is a little grainy, so you probably can't see them, but they're little, basically you can see the eclipse through every pinhole. So they tried to capture those. Unfortunately, the UV was not strong enough during the eclipse to capture a lot of those. So they got a lot before and they got a lot after, but not during the eclipse. So it was just really interesting to have this different view.
Yeah, and I'll jump in there and just say that since we are 2 teams, I'm the lead of one team, and then we have 2 art professors co-leading the other team, and they're Kimberly Ritchie and Aaron Sweeney, both art professors at Plymouth State. And Kimberly and I have collaborated on art and science on projects in the past, and you know, we both find the merging of art and science really important. You know, art is a very important way to help to visualize and give life to what we're studying and what we're learning. So this is something that we, you know, immediately thought, you know, hey, we should collaborate on this, and so it's been a really good partnership, and we get a much bigger range of perspectives on everything that we're doing. From the art students, we even have a poli-sci student on the team, so we really want it to be interdisciplinary in every way.
So getting into the science of it here, it's real science. What is a solar eclipse? For those of you that don't know, it's when the moon obscures the sun in the sky, and some people may not know, the sun in the sky actually moves faster than the moon. So the sun is actually moving behind the moon. The moon is not moving in front of the sun. I guess you could say that depending on what angle you were looking at it. But the moon is actually moving slower in the sky, which is what causes that solar eclipse. So we personally were looking at an annular eclipse in October during the 14th. You'll see a lot of data from that earlier. So you can see that an annular eclipse is when the umbra, the shadow of the moon being covered up, it hits, it doesn't actually hit Earth itself. It comes to a point and crosses. So you're actually getting the antumbra hitting Earth. And that's because the moon's orbit is not circular, it's elliptical. So when the moon is further away, you'll get an annular eclipse. That's during apogee. And when you get a total eclipse, that's during perigee. So the moon is it's closest to the Earth then. So you actually have the actual shadow of the moon hitting the Earth. And that's what gives you a total solar eclipse. So we have contact points. These will become important later. I will also show you this slide later, so you do not have to memorize these. But first contact is when the moon and the sun first touch. Second contact is when the right side of the moon hits the right side of the sun, or the right side of the sun hits the right side of the moon. Maximum annularity or totality, if it was a total solar eclipse, is when it's perfectly covered. Then third contact and fourth contact is just moving back through those as the sun keeps moving past the moon. So the last total solar eclipse in New Hampshire, there was one in 1959, I'll get to that in a second, but there was one in 1932, and they had a citizen science journal written about that. They had people write in during and after the eclipse about what animals around them did during that eclipse, which was really interesting, and we were able to actually read through those. The animals went kind of crazy. Some of them were weird reports, like some guy just shot a snake, and he wrote in about that. He was like, I saw a snake and I killed it. And then there was one in 1959 that went right over New Hampshire. It actually started in the Northeast there, you can see that. But it was not really visible because it happened 5 minutes after sunrise. It was just kind of a continuation of nighttime. So not a great solar eclipse there. But now you have these. So obviously April 8th of this year, you have a solar eclipse going right through New Hampshire. We're all very excited for that. We'll go into that a little bit later. And then the next total solar eclipse that is going over New Hampshire, that's not the next one in the US, but the next one over New Hampshire is in 2079. I will be 77 years old. That's a long time from now. Please go see this eclipse. It's very important. These do not happen very often. So in preparation for these eclipses, Genevieve here did almost all of this work. She made this entire presentation, all the graphs you'll see. I did none of this work, so please don't accredit this to me. But Genevieve did all of these balloon trajectories. So she used the GFS models, so the Global Forecasting System. Global Forecasting, what does the S stand for?
Oh, yes.
System?
Yeah.
Global Forecasting System. She used historical data there to find out where we thought the balloons would go. And that's important because on the other side, on the right side of this picture, that's the Texas border, and that little gray square there is the White Sands Missile Range underneath Albuquerque there. And I don't think the military would like it very much if we were launching 30 or so balloons. We were actually a super site, so we were launching, what, a balloon every 12 minutes?
Every 12 minutes.
So it was a lot of balloons going over New Mexico there, so I'm sure the military wouldn't have approved of that very much. So we tried to make sure we were out of the way. That's kind of why we chose Moriarty. So it was just interesting to see some of these balloons are traveling hundreds of miles. And this is just another trajectory. This is from SUNY Oswego. I believe this was an actual balloon that they let go. Is that true?
This is just a trajectory.
Just a trajectory. But you can see that these balloons, they rise pretty linearly. That little steep section there is actually the balloon turning into the screen and going more north. But these balloons rise to about 30,000 meters. They go real high up into the air, and sometimes, in some cases, they'll go 31, 32, 33,000 meters, depending on the balloon. Some of them just survive longer. We had one pop after like, what, 20 minutes one time in the air. So some of them survive, some of them don't. But you can see it takes about 2 hours for the balloon to get all the way up there, and then an hour after it pops for it to fall all the way back down to the ground. And it's got a parachute. That's why it takes a little while to get back down.
All right, so like all of the other atmospheric science teams, we used balloons and radiosondes, which you can see the setup over here on the table. So the top of our, we'll start at the bottom. The bottom down here, we have the radiosonde, which is what Dr. Kelsey is holding.
And you can pass it here. I'll pass this around. You guys can look at it, touch it. You know, we're not going to use this for research or anything. So don't worry about breaking it. And you can even take the top part off and see the computer chip in there. And whatnot. So
We're also going to hand around this if you have a latex allergy. Don't touch this balloon. Heads up.
But so the radiosonde, which is the little white styrofoam box, is used to measure the temperature, dew point, and pressure. And then it's communicating with satellites all the time to triangulate its position using GPS. Using 3 satellites to locate its latitude and longitude position as well as its altitude. And it uses the GPS to calculate the wind speed and direction, as well as the height and altitude. Then above the radiosonde, we have the derailer, which is pretty much just this little spool of string with a green balloon on it, which the point of the balloon is just to keep the string from knotting.
for catching on the wooden spool.
Yeah.
Splintered.
Yeah. But it's really important to have this spool. Excuse me. The spool of string is really important to make sure that the radiosonde is far enough away from the balloon so that it's not being affected by the air movement around the balloon as it's going up.
And the radiosonde can swing and
Yeah.
pop the balloon, so we like to get it as far away as possible.
And then last, in the middle, right below the balloon, we have the parachute, which is just kind of like one of these green Army Man toy parachutes, but it's red. And then also on the surface, we have the Luft, or the Surface Weather Station, which, as Dr. Kelsey said, is about 2 meters above the surface, or about 6 feet. And this measures the temperature, relative humidity, wind speed and direction, pressure, and the solar irradiance. And it records these values at about 2-second increments. So we have a lot of data from this. So this is just a closer look at the radiosonde and just some of the instruments on it. So at the top here, it's called the thermistor, and it's what measures the temperature. And then next down in this little square, we've got the sensor that measures the relative humidity. And then within the box is the computer chip, which communicates with the satellites to determine its GPS position, which then calculates the wind speed and direction and the height and altitude. And then also in the box is a barometer, which is an instrument that measures the pressure. And then using this little antenna here, it communicates that back to the ground station, which I'm going to now. So the ground station, or the GSU, is this black box. Has a battery and some like computer kind of hardware inside. Here it is in the field, and we were using it during practice launches. And it works by communicating to the radio sound and then outputting what it receives to a laptop. So the radio sound, again, connects to the GSU, and it communicates through an antenna that you put on top of a tent or on the edge of a table. It's pretty flexible. And then the radio sound is communicating to the satellites to determine its position. And then all of the data that it's also recording while this is happening, the temperature and relative humidity, is then communicated back to the GSU and then onto the computer to plot the data in real time.
I'm going to take this brief pause in our discussion for a PSA. Because we're a NASA-funded project, NASA is requiring us to, whenever we do an outreach event, to figure out how many people come and also what zip code you're from. That's all we need. So I'd like to just pass around this notepad, and all I need from you is your zip code. And then, you know, if you came as a couple, for example, and you're from the same zip code, you can just write it down once and then write number of people in your party next to it. Okay? Please do that. Fantastic. It'll make NASA very, very happy. And then we'll be able to brag about the stats that we reached, 500 people through our outreach and all that stuff. So thank you. All right, go ahead.
All right, so looking at a little bit more of a broad view of what was going on at this time, this is starting on October 13th, so it's the day back there, please. This is the day before the eclipse. This is the wind about 1,000. Okay, how are we going to talk about this? We were
about 1,000 meters above ground.
Yes.
Yep.
Okay. So this is the wind about 1,000 meters above the ground. It's at a certain pressure level. The greener areas in this plot are where the wind speed was a little higher, and the blue areas are where it was, pretty low. There's generally, the wind was, I should go on the side, going this way across New Mexico this time, so kind of just from the northwest. And then a little lower down, it was really calm. It wasn't really doing much. There wasn't a lot of wind going on.
Yeah, and you'll see a continuation of that trend. So this was just interesting to see going into launching balloons and understanding when we were launching these balloons up in the air. If you go through all of these slides here, there's almost no wind when we were launching these balloons up in the atmosphere, up to 700 millibars. So we were looking at the speed and direction. We were getting all of that radiosonde data from that radiosonde that's being passed around. And it was just interesting to see that there really wasn't much wind. There was about, I believe Dr. Kelsey was saying, there's a low pressure system. If you go back one slide, back to the first one, there's a low pressure system there that was moving through to the east. And in those slides further on, you can see that it's just kind of pushing on through and the wind dies down. There was almost no wind at the surface most of the time that we were there.
This was a practice trial run so people got used to launching this routine, is that right
No,
statement?
this was us in New Mexico during an eclipse, an annual eclipse.
Okay.
Yep. So you'll see that in a second. Go ahead, Genevieve. So again, I will remind you of these. First contact, second contact, maximum annularity. It's a little grainy on the next slide, so you might not be able to see them, but they're going to be blue lines on the graph. So I'll point them out when we get there. Go ahead, Genevieve. So this is the solar radiance for that day. This was the solar radiation coming in. So this is the first day. I know you can't read these numbers, but this was the 13th, and that's when the eclipse happened on the 14th. So obviously at night, there's no solar radiation. During the day, this is what a normal day should look like. And then you go over that day there, and you can see there's that big dip, right? So that, the solar radiation cut out. That was the eclipse. So if you go to the next slide, you'll see first contact, closest to me, second contact, third contact, and fourth contact. And right in between second and third contact is when the eclipse peaked. So mostly what we were looking at using radiosonde data and the Luft, we were looking at what the temperature was like at the surface, what changed, what the relative humidity was, and we'll go into that in a second. The temperature, go ahead. The temperature, here's a normal day of temperature. It goes up and up and up. Obviously the sun heats the ground heats the air, it keeps going. And then after the sun goes down, there's a bit of a lag before that temperature goes back down. And you can see that the lowest temperature is there right before sunrise. Lowest temperatures are typically around 5 minutes after sunrise. So sunrise happens, solar radiation goes up, and it goes up and up and up and up until the eclipse happens. And you can actually see right before the eclipse, there's a little, like, it almost plateaus. And that's actually not because of the eclipse, I found out the other day. That's because there's this little cold air layer near the ground where you have all of this cold air from the night before, and as that cold air is burned off, you have these thermals that generate. So the sun hits the ground, it warms the air nearest to it, and then that air rises. And as that air rises, it hits the free atmosphere above it. And the free atmosphere is actually warmer than that cold air down there, so it can't break into the free atmosphere. So you have those thermals rising and falling and rising and falling, and all that time, that layer near the ground is warming, until it reaches the temperature of the free atmosphere, where those thermals can go all the way up into the free atmosphere, and it takes so much more energy to warm it. So you have that little layer near the ground being warmed very quickly in the morning, and then as soon as it breaks into the free atmosphere, you see it plateau, and it actually gets maybe a smidge colder for a second there. And then you have the eclipse happen, which makes the temperature dive like that. And you can see that there's a lag in the temperature diving. And then as soon as the solar radiation comes back, it takes right back off. So next, I believe we're looking at relative humidity. So we plotted that over this. So New Mexico, very dry, not very fun. I got a lot of nosebleeds, dry lips, not a good time. But you can see it's usually opposite the temperature. It kind of does a cross. And you can see that during the day, the temperature is really high, and warm air can hold more moisture than cold air. That's pretty basic meteorology. I learned that last year. But warm air can hold more moisture than cold air. So as air cools off, it actually dumps out the moisture into the atmosphere. So you see, as the night happens, that relative humidity shoots up to, at some points, 55%. I don't think you guys can see the percents on the side there, but that's over 50. So you have relative humidity being near zero during the day, and then it going right back up. So you can see during the eclipse, the relative humidity actually went up because the air cooled down and it dumped out that moisture. I believe next we're looking at wind. So we've got a normal day of wind here. I know wind is kind of crazy. It's all over the place. It gusts. That's just how wind is. So you have a normal day of wind. The wind's going crazy, crazy, crazy. As soon as the solar radiation cuts out, the wind dies down. That's a normal cycle. Just because of those thermals that I was talking about earlier. So you see, when the sun comes up on the 14th there, the wind picks up, and it's because of those thermals. So as you have air rising, the air has to come back down, and you get wind from that. So as soon as the sun cut out during the eclipse, you see that wind dive straight to zero there. These are in meters per second. What did it go up to? It was only about 2 or 3 meters per second. But during the eclipse, it totally died out, which was pretty interesting to see. That's all I have to say about that. Go ahead.
All right, so this is just looking at the day of the eclipse. It's the same general plot as the one before. The blue areas here and here are where there was a net radiation deficit. So there was more radiation leaving the Earth than there was coming in from the sun. Which would cause the general environment to want to cool, which we didn't see, but that's okay.
Yeah, those were estimates using
Yeah.
Yeah, some back of the envelope calculations.
Yes.
Yeah, it didn't line up perfectly, but.
And then where it flips to be these red bars underneath is where the net radiation balance was positive, which meant there was more heat from the sun coming in than there was radiation leaving the Earth.
Yeah, so that red section should have continued through the day, but because of the eclipse, right, it was cut in half. So the radiation dropped not to zero, but pretty close to it during that annular eclipse.
And then just to summarize with some actual numerical values for what we saw, the solar radiation dropped 346 watts per meter squared in 1 hour and 13 minutes between here and annularity. And then the temperature dropped 1.2 degrees Celsius in 40 minutes. Just, I think that was this point to down here at the minimum, just past annularity. And as you can see, it did lag. The lowest temperature was observed past annularity, and this lag was about 6 minutes. And the relative humidity, as Jacob said, it did increase after the eclipse. And that increased by 3.1%, and it did this in about 31 minutes, and this lagged the solar minimum by 9 minutes. And then the wind speed also dropped as we expected. It dropped 3 meters per second in 1 hour and 18 minutes. And that's just the point from when it was the highest before annularity to the lowest point around annularity, and this lagged the solar minimum observation by 6.5 minutes. This is a plot of the wind speed and direction, again from the day of the eclipse. The direction is given by the each dot's position on the y-axis, so any ones that are around up here are north, down here is also north because it is out of 360 degrees. This line is generally east, right in the middle would be south, and then up here, about 75% of the way up, would be from the west. And then the color of each dot indicates its wind speed. So the more purple colors are closer to 0, and the yellow-green colors are closer to 10. And there were quite a few interesting features we saw with the changes in wind speed and direction. So around first contact, we saw that the winds were generally from the southeast. And also at this time, the sun's position in the sky relative to our location, which is this black dot that you kind of can't see, the sun was also was to our southwest.
Southeast.
6 years of school, you still don't know what's in this. Anyways, this caused the sun to really effectively heat the terrain to our west and northwest. And when these sides of the slopes are heated, it causes the air on the slopes to be warmer than the surrounding environment, resulting in it rising and the air from the surrounding area to funnel towards the location of the rising air, which is why we saw the wind being from the southeast. And then a little later, following the same general trend, but now the sun has moved a little further south, you can see that the terrain more to our northwest was heated more effectively, which caused the shift in wind speed to be more from the south-southeast. And then around annularity, which is when the sun's radiation was totally cut out, so that whole heating pattern was really not relevant at this time, the wind direction shifted back to what it was originally around first contact because the slopes to our west were heated preferentially. They're heated more before the eclipse, so the air was likely still a little warmer than the surrounding environment. And then a little later, past fourth contact, we saw the wind actually come from the north, which was a little unexpected, and this is likely due to just the complex terrain of the area that we just don't understand.
More to learn.
Yeah. And then at the the end of the afternoon, if anyone was wondering, we saw this crazy increase in wind speed, and it snapped to be pretty much directly from the west, which doesn't really line up with our nice solar heating pattern from before. But if you look to our west, there was ridge lines on these mountains between 2,100 and 2,700 meters above sea level, which resulted in downsloping winds, which is pretty much just when the winds from above the mountain. Would you like to explain this better?
No, you're
Am I doing
you're
this?
nailing it.
Okay.
Yeah.
The wind speeds from above the mountaintops gets kind of like averaged out and mixed down to the surface, resulting in a lot higher wind speed at the surface, and a pretty sudden increase.
We were still launching balloons during that wind increase. If you've ever tried to hold one of these, blown up or not blown up, while it was that windy, it was really not a good time.
We ended up launching an egg-shaped balloon. It got really warped. And then just to summarize some of our data results, approaching maximum annularity, we saw a decrease in solar radiation. We also saw just the expected trends in surface variables that we were anticipating seeing, such as the decrease in temperature, the increase in solar radiation, and a decrease in wind speed. And then we saw some changes in wind direction, which occurred as a result of the mountain slopes being preferentially heated, the complex terrain of the environment, and then we saw the downsloping winds towards the end of the day.
So I know why you're all here. The April 8th eclipse, we're all very excited for it. So we are also launching balloons before that. Dr. Kelsey was talking about that. Here's a path of it going across the US. You can see that the Northeast is actually in that. We're all very excited for that. I'll zoom in on that here. So it goes through Pennsylvania, New York, Vermont, New Hampshire, Maine. If you are not under that path, you will not be able to see totality, unfortunately. So if you are down in Concord here, what are we seeing? 94%, 93%? 96%, even better. But that is not totality. You cannot take off your solar glasses if it is not totality. Don't do that. We're going to talk about that later. So for the actual experiment, we're not expecting very much to change other than obviously the solar radiation is going to drop to actually zero because the sun will be completely cut out. Obviously the temperature will probably drop more, the relative humidity will change. We're not exactly sure though, because we were in New Mexico, we were in a desert, and it's going to be a little different in April in Pittsburgh, New Hampshire. There's going to be snow on the ground, there's going to be trees. We didn't have any trees in New Mexico. So it's going to be a little bit different, we really don't know. Obviously, like I was saying, that's Pittsburgh, New Hampshire, that's where we're going. You can see that red line is the center line, so if you were underneath that, you have the longest chance of seeing the eclipse, which we're pretty close to, so we're excited for that. We'll zoom in here. So this is the town of Pittsburgh, and I believe we're going to be at the Pittsburgh, was that the middle school, elementary school?
It's all in one.
All in one, great. Pittsburgh, New Hampshire.
More booths than people.
So we're going to be launching from what looks like to be a baseball field there, so we're pretty excited about that. It's going to be nice and cold in April, so hopefully we all bring our snow pants. Some future research, I don't know much about this, so Genevieve's going to talk about this. But
Yeah, all right, so like, I think you mentioned it earlier.
Yeah.
Not necessarily us, because this isn't really what we focus on, but somebody else on this project is going to be looking at waves in the stratosphere caused by the eclipse. Would you like to explain the gravity waves?
Well, yeah, I kind of did already, right? If you
Okay.
stick your finger in a pond, right, and just move it along, you get waves, right, ripples. That's what happens up in the stratosphere too, as that eclipse shadow moves across the stratosphere and prevents warming of the ozone layer. And if there was enough water vapor up in the stratosphere for it to condense out into clouds, this is what it would look like, right? These are actually clouds down in the troposphere, probably only, I don't know, 10, 12,000 feet off the ground. So pretty low, and because there's a lot of water vapor here, it condenses out and you can see those actual waves in the atmosphere. But like I said before, no water vapor up in the stratosphere, or very little, so you don't get the clouds and you can't see them. Yeah.
For those of us who are not meteorologically inclined, can you define what the stratosphere is? And it's way up there.
Yeah.
I don't know where it starts and ends.
Yeah, so have you ever flown in an airplane? Okay, you get up to about the jet stream level, which is the very top of what we call the troposphere. the layer of the atmosphere that's roughly 35,000 feet deep, where all of the weather occurs. All of the weather that you see with your eyes and experience, all that's occurring in the troposphere. Once you get above that, that's the stratosphere. So that's where the ozone layer is that I mentioned. That's protecting us from UV radiation. And like I said, there's just not really any water vapor up there. So we don't see anything in the stratosphere. So it's just, yeah, just looks like sky, blue sky. Does that help? Okay, great.
Just one other quick question.
Yeah.
Boundary of space, about 64 miles, is that the top of the stratosphere?
No, there's actually several more layers to the atmosphere above that. There's the mesosphere, the thermosphere, the ionosphere. Lots of different layers that have different properties, thermal properties. They're made up of different gases. You know, the higher up you get into the lighter and lighter gases like hydrogen and helium. And you don't have the heavier molecules like oxygen that we're breathing in, or nitrogen, or carbon dioxide. Those are all down here because they're heavier. So no, the atmosphere goes way, way, way above the stratosphere. Yeah.
Yeah, this is specifically what we were looking at, and specifically what this presentation was about was the planetary boundary layer response to eclipses. So we were wondering what goes on to the weather when eclipses happen. How does the temperature change, relative humidity, pressure? I think that's kind of what the radiosondes helped us with. They go up way into the atmosphere and they take recordings all the way up. So we were able to get really high profile data of that whole section.
Also the boundary layer, for anyone wondering. So just above the surface, up to about 2 kilometers above the surface, that's the boundary layer. It's the lowest, about 2,000 meters at 6,000 feet. Yeah, about 6,000 feet of the atmosphere.
And it's called the boundary layer because it's the layer of the atmosphere that responds quickly to surface conditions. So when the sun comes up and heats the ground, it's the boundary layer that warms up. Or at night, when there is no sun and the ground is cooling and cooling the air above it, it's that shallow layer that's getting cold, that's the boundary layer at night.
Yeah, so when I was talking about the thermals earlier, I was talking about a small layer. It's actually 2 kilometers deep, but that was what was being heated before the free atmosphere. So if we go back there, because we had that temperature plateau, that was actually the residual nighttime boundary layer there that was being heated, and then it broke into the free atmosphere there. So I was talking little, some of you might thought, I don't know, a couple feet or something like that, but it's actually 2 kilometers thick.
All right, and then this is my kind of personal research after the eclipses. So for my master's thesis research, I'm going to be comparing how weather models handle eclipses. This is just a plot showing the difference between 2 weather models that I ran. So one is with a setting that acts as if the eclipse is happening. So it cuts out the solar radiation for the duration of the eclipse. And then I ran one without that setting. So just as if it were a normal day. So full solar radiation, nothing special going on. So this is a plot just showing the difference between the temperature in the 2 models. So it's in the areas where the shading is blue is where the eclipse predicted, or the model with the eclipse turned on predicted that it would be cooler, and these areas where it's red are the areas where the eclipse turned on model was warmer than the model without the eclipse.
Is that blacked out Moriarty?
That blocked out is Moriarty.
Okay, and we're looking east-west, so those are the mountains?
Yes, it's
to
a
the
cross
west,
section.
on the left side? Okay, yeah.
Thank you.
I told you we'd go back to eclipse safety, and here we are. Always wear solar glasses when you're looking at the sun. It is not safe to look at the sun. I'm sure if you come here during the eclipse, they'll have solar glasses. I know that they're selling them in the gift shop. I don't think it's open right now. Is it?
We can have Kelly open it.
If you need solar
If you need
glasses,
we
yes.
can have them ready for you.
I would highly recommend getting them.
Don't wait.
Don't drive home with them.
Yeah. And don't wait.
That's what I'm saying. Don't wait. Get them as soon as possible. April 8th is fast approaching and you might not be able to get them by then. Just please be safe. If you're not under that totality line, you cannot take off your solar glasses when looking at it. And then just a few more resources here. Obviously, we've got the National Eclipse Ballooning website because that's what we're doing. We've got NASA. GreatAmericanEclipse.com is a great website. This guy's got a shirt from it, a hat from it. He's got all of it. The bag from it. But it can really just show you where the eclipse is going to be, where the future eclipses are going to be, everything like that. And you can zoom in on each state. So you can see exactly what towns are going over. Just really great website. I believe that's it. If anybody has any questions, please go ahead.
What was your biggest surprise down in New Mexico?
What was our biggest surprise?
Other than the fact that it was really, really dry, which you can prepare for, but it seems like no matter what we did, we were not prepared for how dry it was. I guess the biggest surprise we saw was the really strong increase in winds at the end, which wasn't necessarily an eclipse response, but we were not anticipating that.
Yeah, the winds got really gusty, and that combined with the dry air, my eyes were hurting because they were drying out. It was so dry. 5% relative humidity is extremely low, and we can only really achieve that indoors in the winter time around here. It just doesn't really happen outside. We're such a humid environment.
What happens is there's a layer of clouds in.
Oh,
During the eclipse?
You still should wear your glasses.
yes, yeah, you still need to wear your glasses, that's for sure. Yes.
Is there any research to other layers of the atmosphere, like the ionosphere? Are we looking at chemical composition changes during the eclipse?
We are not. Some of the engineering teams could be, but I'm not sure. And I do know that that is an area of research that people I don't know are doing. Yeah, I just can't speak to it. In the back.
What are some of the applications of soil sage?
Yeah, well, Genevieve's is one. Wait, oop, well, that-
It's on wheels.
I'll stay on my feet. Looking at how weather models perform with and without the eclipse, so we can learn more about how to improve weather prediction is one. And then just trying to better understand what's going on up in the stratosphere. This is definitely a new area of research, and we don't exactly know what these waves in the stratosphere are doing, how they're impacting other things going on in the stratosphere or even down into the troposphere. It's a big unknown. Yeah. You had a question too,
I
right?
did.
Yeah.
I still do. The graph that you showed that had the multiple pieces of it with the wind speed, temperature, and all that, was that the 2017?
That was this October,
That was
October
the
14th.
October. Okay,
Yep.
got it. Okay.
So we traveled to New Mexico to see that.
My question was, and probably the answer is obvious, but I went to Hopkinsville, Kentucky for the 2017 eclipse and videoed it and did a temperature recording in Fahrenheit, and it went from 111 down to 82 in Fahrenheit. And so I was curious why the temperature drop was not so much, and I imagine two things, correct me if I'm wrong. It was drier there, number one, and number two, it was an annular eclipse and not a total eclipse.
Well, so you also have to look at the time of day. So that was pretty early in the morning. What was it, 10 a.m. when the eclipse happened?
Okay, good, because
So-
this was like 1:30 in the afternoon.
Yeah, so 1:30, the troposphere has time to heat up, right? Like the
Okay.
area around you has time to heat up. You have a lot of hot air, whereas it was still pretty cold.
So in 111 degrees sends up a little red flag, especially in Kentucky.
Yeah,
Right, lots of trees, it's a humid environment, so a lot of the solar energy coming in actually goes into evaporating water and not heating up the ground and heating up the air.
Yeah.
So that makes me wonder, where was your sensor located relative to the ground? Because the closer
on
to
a
the ground.
chair, 2 feet above the ground.
Yeah, so boom, that's the reason why you saw a big temperature drop. So the
Okay.
closer to the ground or another surface that it's sitting on that can get heated by the sun, the hotter it's going to read. So whenever you see, on the news or, on your favorite weather app, what the air temperature is, that's being measured at about 1.5 to 2 meters high. So
Okay.
around 5 to 6 feet. That's where it's being measured. If you were to put that same temperature sensor down near the surface, it's going to read a lot warmer when it's sunny and colder on a clear, calm night. Because it's the ground that gets warmed by the sun, which then warms the air. So the ground can get really hot. Think of an asphalt surface on a summer day, right? That is way hotter than the 90 degrees that you're feeling up here by your head, right? So that's why you saw a big temperature change there.
Good, thank you.
And that's also why the loft is 2 meters above the ground, right? It's off the ground. That's where we wanted to record those temperatures. And it's actually blocked from incoming solar radiation, right? So you're not actually getting the temperature of the solar radiation coming in. It's getting the temperature of the air coming in from the side.
Goes back to the application that somebody else asked. I was trying to follow what the temperature and the wind differentials were as you went through that. I think once you get all your models set up, is it something that you could think, you were over land both times? Some of those trajectories also were on coastlines and water. Could it help prevent flooding if you knew, like, if your wind speeds changed enough or temperature changed for waves, could you help prevent flooding? Some plants are very temperature sensitive. 1.2 centigrade, I think, is one of the changes were. It doesn't sound like a lot, but I think some, the difference between 33 and 31 degrees for some plants is dead. So is that something that there's enough data to start working on those types of crop protection or flood protection?
I would say because it happened during the eclipse, eclipses only happen every once in a while,
It's
so
not
there's
that big a
not,
deal.
we can't control the eclipses, and I wish I could make them happen all the
But
time.
you
I wish I
can
could see them.
you can work, I'm trying to think of like
Yeah,
the other question in practical applications for
Yeah.
the data use. Is that something that?
I think so.
I have a sort of related question. Maybe some of the research has gone on with volcanoes exploding and blocking out localized sun for longer periods of time. Would that relate at all to this research?
A little bit.
Certainly it's having the same effect, yeah. But of course with volcanoes, for example, that ash gets, especially with a very explosive volcano, that ash can get up into the stratosphere where it can hang around for up to 3 years. Yeah, so it can have a very long lasting impact, whereas an eclipse,
It's 4
only
minutes.
a couple hours, yeah.
Are you guys watching this morning for the groundhog announcement?
Early spring.
Will that affect your, and actually, no, I actually have another question. I'm curious if you've heard any, what's the wildest cultural, I guess, myth about an eclipse that you can tell us that you've studied or?
No, you go.
They, I forget exactly who it was, maybe it was the Aztecs. They used to think that they needed to kill their king to get the eclipse to go away. So they would actually appoint a fake king for the day, and he would be paraded around, and then they would kill him at the end of the day, which was pretty interesting and not a good way to go, but I have to imagine he had a good day.
Up until the eclipse.
Yeah. Oh, yeah. Yeah, what do you got?
Are you limited under, I know we're all hoping for clear skies, but somewhere along the path, possibly where you're launching balloons, it may not be clear. Not in New Hampshire, but one of your other sites. Are you limited by wind or weather, or have you tested, are you able to go up in just about any weather? Because once you get above any weather, if that's the area you're shooting for, so I'm just wondering, will you launch in any type weather conditions, or have you experimented with that?
Really, the only hard part about it is launching the balloon itself, right? And that's why we picked those big fields. In New Mexico, there weren't any trees. We were in a massive field. You can actually see in that picture there, we were practicing at the Plymouth airport. I know, Plymouth has a little airport. It's tiny, a little grass runway. But putting it in an area that there's not anything to pop it, and we have a big sheet that we can put over the balloon to hold it in place. But that matters a lot. But once it's off the ground, not really.
I've been to Pittsburgh, there are a couple trees over there.
Oh yeah,
just to let you know.
That's why we're in that baseball field. So we're hoping to get as much clear area as possible to launch the balloons in.
And if the wind is going this way, go to that side of the field. Yes. A secondary question, did you have any contact with the Albuquerque Balloon Festival? Did any of your balloons?
Yeah, so we were there during the Albuquerque Balloon
Yeah.
Festival. Yeah, you want to speak on that?
Yeah, we didn't want to interfere with their balloons, and we didn't want their balloons interfering with our balloons, so we purposely positioned ourselves away from Albuquerque.
Okay,
Yeah.
so you were far enough away. There was
We were.
Yeah,
In
we were
fact,
about
we
40
couldn't
miles,
see
yeah.
the balloons from
We
where
saw
we were
one balloon.
because- Yeah, one rogue balloon, probably from somewhere else. But the mountains got in the way from us being able to see the balloons go up.
The terrain around Albuquerque kind of makes a bowl so that the winds, so that the balloons can't really get outside of the bounds of the mountains. So if we were on the other side of the mountains, we were good.
And it's that geography that makes Albuquerque a great place to host this balloon fiesta every year. That's why it was chosen. And another thing I wanted to mention about the weather, safety's number one, right? We want everyone to come back home safe and sound. So if there's thunderstorms, right, lightning, we will not go outside. We will go back inside and seek shelter until the threat passes. So as long as everyone can be safe, then we will release balloons. There are certainly limitations to our equipment. If we have a 20-mile-per-hour wind and driving rain, we probably will close up the laptops and bring them inside until that threat passes so we can keep the electronics dry. That being said, my colleagues and I have launched balloons in some extreme conditions before. You might remember the October 30th flood of 2017, I think it was, 17. Up in Plymouth anyway, we had flooding, but during the middle of the night, we had pouring rain. I think we got 3 or 4 inches of rain across basically the entire state. And my colleagues and I went out at 2 in the morning to launch weather balloons in the pouring rain and winds that were gusting to 60 miles per hour.
Wow, so
Yeah.
you're gonna launch.
We found the limits because we did not get a successful launch. A balloon popped, another one got caught in a tree, and the other one blew somewhere over the hill, and we lost contact with it right away. So, yeah.
So another thing about these balloons, they're actually biodegradable, which is good. So when they pop, when they get up to 30,000 feet, they will shatter into hundreds of little pieces and fall down, and they can biodegrade as fast as, a month? And then the radiosonde, the radiosonde itself is styrofoam, and when we were launching, we were actually writing on the back of it our address. You could send them back to us if you ever found them. The government used to do that. You could send them back to the government, and they try to reuse them, but I don't believe that they do that anymore.
They don't reuse them anymore. In fact,
They don't want to be found.
the National Weather Service launches these same exact radiosondes that you just looked at.
Has anyone ever thought it was from China and tried to shoot it?
That's what we were worried about.
Yeah,
5 years
well,
ago, yeah.
maybe in Texas, I don't know.
Did you get any back?
No, we did not get any back. I don't think yet, right? And most of them landed in the middle of the desert, and there's actually a website online that you can track them and try to track them down, and it'll get them within 20 feet of hitting the ground or something like that.
Yeah,
So you can
a little more than that.
but
yeah.
you can still find the parachute and everything like that somewhere. But we have not found any. You tried to chase after one time.
Yeah.
They go hundreds of miles, so sometimes you really can't go find them.
What's the range that they can report back?
So they use radio towers, right? So we use a frequency. So we actually had to be careful because the Albuquerque National Weather Service office was using frequencies too, and we were a super site. So we had to really space out what frequencies we were using. So it doesn't really matter, as long as there's a cell tower that it can connect to somewhere, it can keep connecting back to us.
No, it's line of sight with our
Line of
antenna.
sight?
Yeah.
Oh, okay, never mind.
So if it were to go behind a mountain and we lose a line of sight with it, then we lose data. Yeah. You have a question?
Yeah, I think I have a few questions here, I'm not sure yet. So if we were looking at the map of the United States up there, then the totality is gonna be moving toward the southwest, is that correct?
No.
No, northeast.
It's gonna be
north.
moving up toward the northeast?
Yep.
Okay. So,
What time of day is it supposed to start?
yeah, that's a good question.
Sunrise.
Here,
Well, here.
it peaks, totality is around 3:30. in northern New Hampshire. It starts about an hour and a half. or
2
so
o'clock,
before
2 to
that.
5 is the total event.
PM or AM?
So,
Yeah.
You're gonna be able to see.
Sure.
so you guys are gonna be, I mean, the prevailing winds are always from the west, and you guys are gonna be on the fringe, and it's gonna be moving away from it, and so have you got guys on the other side of totality that are gonna be blowing into it, as, assuming the westerly wind?
Do you want me to take that one?
Yeah, go for it.
You pick the location.
So for the atmospheric science teams, we just want to be on the path of totality. We want to see totality, right? We want to see that. In terms of taking good scientific measurements, it doesn't really matter too much because those stratospheric waves, for one thing, emanate for hundreds and hundreds of miles. So it doesn't really matter where we are, as long as we're kind of in there.
Okay.
We'll be measuring those stratospheric waves. And for the surface effects, right, they're going to be most pronounced under the path of totality for annularity for back in October. So that's another good reason to be right under the path.
Right. So I was gonna ask if you had to factor in latitude and so on to compare data points from each different location. Because they're all gonna be different based on just where they are in the terrain, latitude and so on. So you have to do the extra calculus for that or something?
Yeah, so we have, well, those 19
So that you can
atmospheric science
compare data
teams.
with data?
Yeah, they're all strung across totality. I believe all of us are under totality for the April 8th eclipse. So obviously we have the coordinates in the town and where you launched. Like that's why we know exactly where that Pittsburgh baseball field is, because that's where we're going to be launching from. So we're going to send, I believe, all that data back to NASA and let them sort through it, right? Like that was their ultimate
We
goal.
are. We're going to sort through it.
Yeah.
Yeah, all the teams on the project are going to.
Oh, great.
We're going to look at it.
That's nice.
Do you have any teams in Canada or Mexico?
I don't believe anybody's leaving the US.
Largely because it's a NASA funded project.
Yeah, I was just curious because it goes over sunrise, sunset, different. Yeah, it's a long day.
You have a
I'm
question?
gonna be about a half hour away from you guys. Is there a plan?
You can try. At this point, I don't know what the school is going to want to do in terms of the public coming in and out. Pittsburgh School has canceled classes that day, it's a Monday, and they're going to just celebrate the eclipse and have eclipse activities going on. We're gonna be there so the students can come and learn from us while we're launching balloons. And I heard from my point of contact at the school that in Pittsburgh, they're actually going to shut down Route 3 during the eclipse.
I think other state footprint.
Yeah.
You wanna, I'll be there Thursday, so you wanna arrive, if you do travel, please arrive early, leave late. Don't plan on coming up Monday morning and getting back Monday evening, because you'll never get near totality if the weather's nice. It's great.
Are we staying Monday night?
Oh, we are.
Yeah, so we're
You want to know?
Yeah, in fact, from the 2017 eclipse, we learned all across the country with so many people, millions of people crowding along that tiny path, that most places saw traffic they have never seen before. People couldn't get anywhere for hours or even days. Yeah, it was really bad. Worse than any other, big sporting event you can think of, like anything. It dwarfs everything.
And they don't have great roads up in Coast.
Yeah.
Just as a.
It's during mud season
There'll
too.
still be snow up there.
There could be, yeah.
We're planning on it.
There'll be snowmobiling up there in April.
I believe that Concord is looking to get some kind of legislation to actually do something about changing the time of the school day.
Not
Because of the
happening.
eclipse.
We
Yeah.
tried,
No,
we
failed.
were
They
there.
failed?
Failed.
Okay, alright. Well, I got shot down.
17-3.
Oh, really?
In committee, yeah. Although there's Senate Bill 105 that was signed by Governor Sununu in August of 2017 declaring Monday, April 8th solar eclipse day in New Hampshire. So there is a bill on the records, and it recommends educational activities, and the school system of New Hampshire is working on getting solar eclipse classes for students, but it takes the government a while to get back to me, so
Yeah.
I'm waiting. And there's I'm sorry, I misspoke earlier, there are not 63 days to Monday, April 8th, there are 66 days. So 66 days until.
Use those 3 days wisely.
Well, if that's it, thank you all for coming. We really appreciate you coming.
Thank you so much. So next on our agenda is a 10-minute break. You can use the restroom, get some water, look around, and in about 10 minutes, make your way down to the Planetarium Theater, and we'll have a planetarium show. We'll show you an actual